Welcome to this e-learning module UR-103 FlexLogic. In this module we'll cover the following. Section 1 will be an introduction to FlexLogic and its components. Section 2 will cover the Logic Designer menu where we will create some simple circuits. In Section 3 we'll review the operation of the equations using the Logic Monitor. Next we'll take a look at the Preferences screen that provides some changes to the Logic Editor appearance and functionality. In the FlexLogic equation editor, we'll review some of the logic that we've created. In resources, we'll show you where to find more information about FlexLogic. And finally, I'll create some additional FlexLogic examples. Power system protection and control schemes using protection relays are based on logic. A multifunction relay, hundreds or even thousands of logic elements and equations are required to make decisions on the state of power system and to generate pre-planned responses to system events. The UR uses FlexLogic to allow for customization of the protection and control within the relay. FlexLogic is based on Boolean algebra that allows the customization through a series of equations. These equations consist of operands, operators, and outputs. The operands are evaluated by the operators, and the resultant provides an output. The equations are based on the reverse Polish notation, which means it begins with entering operands or some type of input, it becomes evaluated, and a resultant is stored in an output. These equations are evaluated every 2 milliseconds. To look at it from a different point of view, here we have 2 contact inputs going into an AND gate, and Boolean algebra basically evaluates the status of the 2 inputs and then provides an output to a virtual output. Operands are any digital or analog signal available in the UR. The operands are inputs to the operators. They represent the state of inputs, elements, schemes, and outputs. Signals such as the contact I/O, virtual I/O signals, remote inputs for the goose, Boolean, DPS, and analog, direct inputs, teleprotection signals, protection elements, push buttons, self-diagnostic alarms, digital elements, counters, temperature monitor, flex element, flex analogs, cybersecurity, and password security. The user has complete control of all variable logic through this FlexLogic. Some of the operands can be renamed in the ID fields such as the breaker control, contact I/O, and virtual I/O. The system receives analog and digital inputs that it uses to produce the analog and digital outputs. Operators are the logic gates, timers, and latches. The operator compares all of the inputs that are assigned to it and sets an output that is based on the status of those inputs and function of that particular gate. Operators consist of the following items: AND, OR, NAND, NOR, exclusive OR, and inverter. The number of inputs are adjustable between 2 and 16 for the OR, AND, NOR, and NAND gates. Other operators consist of volatile and non-volatile latches, timers, and OneShots. The maximum number of OneShots in FlexLogic is 64, while the maximum number of timers is 32. The output or the resultant of the operator is stored in a virtual output. In FlexLogic, the results of the operator are stored in an output. That output is known as a virtual output. There are 96 virtual outputs in the UR. Since the UR is signal driven, the virtual output provides the means to control different functions of the UR, such as controlling LEDs, contact outputs, oscillography, etc. Virtual outputs can also be used as inputs into another equation or logic. There are some guidelines to be aware of though. Once a virtual output is assigned to the end of the logic, it terminates that equation. You cannot use the same virtual output to terminate more than one equation. If you try, you will get an error. In this section, we'll discuss the Logic Designer and the drawing components associated with it. We'll also discuss the compiler and its function within the InterVista application. To access the Logic Designer, you use a settings file that's in your offline window. You expand on it and you go to the engineering heading. The very first thing you see here is the Logic Designer. Double clicking this will open up our Logic Designer menu. Our screen consists of the following. We have the editor toolbar, the basics actions toolbar, we have an advanced actions toolbar, the token toolbox, and the compile manager. These different toolbars can be turned on and off by going up to view, toolbar, and you can switch them on and off by unchecking or checking them as needed. If you accidentally turn this off, you can bring it back on by going to view, toolbars, and bringing it back on board. In the token toolbar, we have drawing tools that consist of lines, polylines, polygons, different shapes. We can add text, we can add an image, and we can also add notes. In the second tab, we have the I/O tokens, which is a list of all our different types of inputs and outputs. Virtual outputs, we have our LEDs, and can actually have some additional tag in and tag out, which is used to connect into other schemas. The number in brackets here indicates these are how many are available. When we start drawing, what will happen is as we start consuming these different gates, the number will be decrementing. Under Boolean tokens, we have our different gates that are available to us, latches, there are one-shots, and timers. And under the last one, we have our elements. So you can see flex elements, settings groups, switch selector. You can also see here how many of each of these are available. To create a circuit, come into what you want to select. Remember, we have to have inputs first, and then our operators, and then our outputs. So we'll start with our inputs. So we'll take a contact input, select it, let go of the mouse button, move your cursor to the middle of the canvas, and click on the left mouse button, and it'll deposit it. If you want to go in and make some changes, you can come in here and go in and make change the name of the contact input. The default factory default is contact input. This we can call it switch A. We can assign whichever input that we want to use. We can add a debounce time, modify it here, and we can also make a note of it to be recorded in the event recorder. We select OK. This name will update. If we choose to select another one, we can. If we want to do some alignment, we can use some of the tools up here. This will allow us to do something like this, where if we select both. The other thing that we have here is we have our contact input. We can add this in as well. When we double click on the contact on this input, we have a choice of menus as to what we can select. You can see virtual outputs, protection and control, monitoring, miscellaneous counters. All of these different items are selectable. In this case, I'm going to pick something simple like the push button. And when I click on the input, it allows me to come in here and select which push button I want to use. If I click on View Associated Screen, it will actually take me over to that particular menu. If I close this down, it allows me to come back, and now I can complete my circuit. So I'm going to assign an AND gate between the two contact inputs. Simple as selecting it, clicking on it. I'm going to put in an OR gate in here as well. When you're selecting these different gates, when you double click on the gates, you have the ability to go from 2 to up to as high as 16. You can select the different types of gates that are available. So in this case, I'll stick with 2. I want the on portion of the switch, so when the contacts close, the output will be active. And you can see how the color changes as I make the connections. So to make the connection is very simple. You move your cursor over to the connection point, click on it, it'll create a crosshair, and when you see the circle around the crosshair, then you click again and it'll make the connection. So I'm going to do the same thing here. To complete the circuit, we need a virtual output, and the virtual output is located in your I/O tokens. Once again, here we can come in and give this a name. Assign it to be to record it in an event recorder. Once we select OK, name it'll update, complete our connection, and this is how we make a circuit. The canvas here can also be modified. If we right click, we can turn on a grid. This grid is also adjustable both in color and in spacing. If we go to grid properties, it allows us to change the color of the grid and allows us to change the horizontal and vertical spacing. Another thing that we can do is we can also change the color of the background. In default properties, we have the ability to change the background to a different color. And the other thing that we can do here is we can also go back and we can zoom the screen to a different size, or we can have it to just fit to the screen. If you want to repeat a symbol, the repeat symbol refers to when you first bring an item onto the canvas. You can select it, deposit it, and then every time you click, it will repeat every time you click without having to come back into the toolbox again. If you want to delete any components, you can just select it and press the delete button on your keyboard. You'll get a message to confirm. Select yes, and then that'll delete it. To modify the circuit, it's very simple. All you need to do is click on the line, press your delete button, it will break the circuit, and let's introduce a timer. So we'll connect our lines again. So once again, we can do a horizontal alignment. So what I've done, I've selected the 3, depressing and holding the shift button to select all 3, and then using the horizontal alignment tool that allows us to do that. The timer can be adjusted by double clicking on it. It'll bring in the timer's name. You have a range of pickup delay and dropout delay. The different time units are milliseconds, seconds, and minutes. So if I do something to the effect of changing this for 3 seconds for a pickup delay and 5 seconds for a dropout delay, and I'll put this into seconds. When I select OK, then the timer will be updated. To have everything fit on the screen, I can right click and get this to zoom to fit. If we want to add some comments or some text, we can come up with drawing tools. We can add a text box that allows us to Once we double click on it, add some text. We can go in, we can right click on it, on the box, change the properties. We can change the font size, the color of the line, the fill, and also the different fonts. The other thing we can do is we can add images, we can add notes. So if we select note, when we double click on the note, it allows us to come in and enter any type of information. Something such as this. So this note now appears up here, and you can see it's got the actual header, feed array. When you double click on it, you'll see the actual note that's associated with it. So let's just adjust the screen again. There we can see the whole thing. Let's talk about timers. In the UR relay, there are 32 timers available to us. Each timer can only be used once. That means two different circuits cannot use the same timer. The range is 0 to 60,000, and then we have choices of units for milliseconds, seconds, and minutes. The inputs can be any logic variable, such as a protection element. We can have any contact I/O, virtual input, or a virtual output as an input to the timer. The way it's broken down is the upper portion is known as the time delay on, and the lower portion is known as the time delay off. If we introduce a quick pulse, then the result from the timer is this. We have a time delay of it turning on for 3 seconds. It will remain on, time delay off for 5 seconds, and then return to the state, to the original state. When we're looking at the canvas here, we have, by default, 4 different sheets are generated. If you want to add additional sheets, all you have to do is just right click, and you can insert more, or you can delete, you can rename them. If we come back in here, one of the things we have to keep in mind that we can have up to 1,024 items in total. So this is not per sheet, but in total for the entire settings file. Now, what is a line of code here? An input or an output. So the push button here is considered 1, 2, 3. The gates are also considered as part of lines of code. The timer, and also the output. So in this case, we have 1, 2, 3, 4, 5, 6, 7 lines of code that have been consumed out of a possible 1,024. Text or any notes or LEDs or anything else that's added on here are not considered lines of code. The flex analog symbol can be used to monitor an actual value from the universal relay. The flex element symbol is a universal comparator used to monitor any analog actual value. With these two symbols, you have the ability to compare a single analog value against a threshold or compare the net difference between two analog values. Now, there are two inputs. There's the non-inverted input, plus N, and the minus N, which is the inverted input. If you were to place the flex analog only on the inverted input, the results displayed on the flex element would have a negative value. Now, when you're using the flex element, the flex analog inputs must be the same. So, for example, if you were to compare the voltage between a main and a tie. As of both elements, there are 3 flags: the pickup, the dropout, and the operate flags. In this example, we'll show you how to hook up a single flex analog and connect it to a flex element. So the flex analog is located in I/O tokens. Select it, put it in. We'll grab the flex element. Now let's go ahead and configure this for a voltage. We can come in here, we can set up our levels, we can give it a name. So I was calling this VAG. We can set up our input modes, whether we want to go signed or an absolute value. We can do a level or delta if we're comparing two signals, and direction, whether we're going to go over or under. Everything is in reference to per unit as opposed to the magnitude. If we're doing a delta comparison between two, then we use this particular menu down here. So let's set it up for 1 per unit. If we go over as a level, this will be signed, then this will become active. So the idea here is once we have this connected, this is everything. So if the voltage level that's measured here, it'll be an analog value, will be displayed here as a per unit. If we redraw this, and we'll show second circuit here, where what we'll do is we'll put this on the negative side to show you the difference. Let's go back and rename this. Call it negative. Once again, it'll be I'll leave it as an over signal so that we can see that, and we'll go ahead and leave it like that. In this example, we'll show you how to connect a single flex analog to a flex element. First, we'll go into the I/O tokens. We'll grab a flex analog, and I'll grab a flex element from the elements. Now what I'm going to use here is I'm going to use the voltage, source 1 voltage VAG. The triple line here indicates that it's not measuring anything yet, so this is why it's got the 3 slashes. On the flex element, I can come in here and name this whatever I want. So let's go ahead and change this to VA. I can set it up as a signed mode or an absolute level or over under. Let's set this up as 1 over per unit. We use the absolute value. And we'll connect this. Now, when measurements are going on, this will show the actual analog value in here. This will be a percentage of the per unit. The other thing is, how will we know if this is active? So what we're going to do is we're going to grab an input, and we're going to assign it to the magnitude to determine whether this is actually operating or not. So what I'm going to do is assign this to the flex analog configuration. So here I have choices of the dropout, the operate, and the pickup. So what I'm going to do here is go with this one, with the operate. If I go select view associated screen, it'll allow me to come into this screen. I can see all the configuration that I have assigned to it. And what I'm going to do is I'm going to assign this to a virtual output. So the next virtual output that's available for me is a virtual output number 3, and I can assign this as VAG. I'll name it as well. And the only thing we need to do is just connect this. The second thing I'm going to do is I'm going to do the same thing, and I want to show you what this looks like when it's set up on the negative terminal. So let's go ahead and copy this. We can copy and paste the whole thing. So I'm just doing a Control-C, bringing the cursor down, Control-V, paste, And I'll just grab the whole thing and shift it over. And the only thing I'm going to do different is I'm going to break this line. And I'm just going to connect it into the negative port, the inverted, and we'll repeat this as well. I'll just drag this down. And I'll just leave this one as virtual output number 4. So that'll be our second circuit. I've renamed it. I haven't done anything different except put it into the negative. I've created an absolute value, except this time instead of being over 1 per unit, I've selected under. So in this example, what's going to happen is the upper circuit is going to be above 1 per unit, and the second one is going to be below 1 per unit. In this example, we're going to compare 2 analog signals again in the comparator with the flex element. So what we're going to do is we're going to take 2 flex analog inputs, and we'll take the voltage again. So I'm just going to copy and paste. So what I'm going to do here is I'm going to take 2 different sources. The second one will be source 2 on the voltage. And we'll grab a flex element. And this is going to be like a sync circuit. So what we're going to do is we're going to compare these 2 voltages against each other as in a main tie. And if the difference between the 2 are greater than a certain amount, which I've put in as 0.1 per unit, then this signal will become active if it's greater than the 0.1. If it's less, then the operate signal will be extinguished. So once again, we'll put this into the plus. Let's go into the minus. And we're going to insert that signal again to verify whether this is activated or not. And we'll come into the inputs. Here's my operate signal. And I'll assign it to a virtual output. There, that completes that circuit. So once again, the idea here is if the difference between these 2 voltages are greater than 0.1 per unit, then the operate LED will the operate signal will be active. Here we'll talk about the volatile latch. The volatile latch looks like this. There are no settings associated with this latch. This latch is reset dominant. If both the set and reset are on, I mean logical 1, then the output is off or logical 0. When using the latch in your FlexLogic, be aware that if there is a loss of control power, the latch will reset. In this video, we'll go ahead and create a simple volatile latch circuit. We'll take 2 contact inputs and we'll bring it into, tie it into our SR latch, our volatile latch. The inputs will be tied, one to the set, the other one to the reset. And to complete the circuit, we need to assign it to a virtual output. One more thing that we'll introduce is an LED. And that completes our circuit. To change your LED designation in your circuit, you can double click on the LED and click on the pull down, and you can pick and choose whichever LED is available. You can select it. You have a choice of either going with the type of either resettable or a latch condition. Once you select OK, the LED is now updated. Here we have a truth table that shows the correlation between the inputs set and reset against the output. If the set is on and the reset is off, meaning on being a logical 1 and off being a logical 0, the output is on. If they're both off, then the state doesn't change from its previous state. If they're both on, then the output is off. If the set is off and the reset is on, then the output is off. The non-volatile latch outlined here provides a permanent logical flag that is stored safely and does not reset upon restart or after the relay is powered down. This latch can be configured to be either set dominant or reset dominant. Typical applications include sustaining operator commands or permanently blocking relay functions such as an auto recloser until a deliberate interface action resets the latch. Here we're going to build a non-volatile latch circuit. We'll take inputs again. And we'll grab our latch, our non-volatile latch. So what we'll do here is we'll set one up as reset dominant and we'll set up a second one as a set dominant. We'll make the target self-resetting and then we'll assign this to a virtual output. And in this case what we'll do is we'll set one up for both the on and the off. And let's assign LEDs to this as well. To align these, we can do the horizontal alignment. And what we'll do is we'll go ahead and duplicate this whole circuit. And what we'll do different here is we'll make this set dominant. That way we'll be able to compare the two. Let's review the truth table for a reset dominant non-volatile latch. If the input set is on and the reset is off, the output on is on and the output off is off. If both the set and reset are both off, then both the output on and output off remain in their previous states. That means it doesn't change. If both the set and reset are both on, then the on output is off and the off output is on. Finally, if the set is off and the reset input is on, then the output on is off and the output off is on. Let's review the truth table for a set dominant non-volatile latch. If the set input is set to on and the reset input is set to off, then the output on is on and the output off is off. If both the set and reset are off, then the outputs on and off remain at their previous states, don't change. If the set and reset inputs are both on, then the output on is on and the output off is off. If the set input is off and the reset input is on, then the output on is off and the output off is on. A one-shot refers to a single input gate that generates a pulse in response to an edge on the input. The symbol here is for a positive one-shot. There are a maximum of 64 one-shots. A positive one-shot symbol responds to a positive going edge in the logic designer diagram. The graph shows the relationship between the input and the output of a one-shot. On the positive transition of the input, a short duration pulse is generated on the output. A one-shot refers to a single input gate that generates a pulse in response to an edge on the input. The symbol here is a negative one-shot. There are a maximum of 64 one-shots. A negative one-shot responds to a negative going edge in the logic designer diagram. The graph shows the relationship between the input and output of a negative one-shot. On the negative transition of the input, a short duration pulse is generated on the output. The symbol here is for a dual one-shot. A dual one-shot symbol responds to a positive negative going edge in the logic designer diagram. It also generates two pulses. The graph shows the relationship between the input and the output of a dual one-shot. On both the positive and negative transitions of the input, a short duration pulse is generated on the output. Here's an example of a FlexLogic circuit to trigger the oscillography capture. The oscillography capture is triggered by a positive going edge. When the IOC operates signal becomes active, it generates a positive going signal that momentarily triggers the oscillography capture. If the next signal becomes active while the first signal is still active, then the oscillography will not trigger again until the trigger level is reset. Let's modify the circuit with one-shots. So if the IOC operate becomes active, it creates a short pulse as a trigger to the oscillography and the trigger is reset. If another condition occurs while the first one is active, the oscillography will trigger for the next condition, and so on. With the one-shot in the circuit to the OR gate, it provides an opportunity for all triggers to be recorded by the oscillography. The compile manager is located under the offline window. The compile manager saves the logic to the settings file. So if you leave this screen without compiling, you will lose your configurations. During the compiling process, it conducts checks for errors in the logic, such as are you using default names? It'll check for inputs without a corresponding output. Are your functions disabled? It makes sure that all your connection points are connected to a symbol. Once it's finished compiling, it'll display the number of saved lines. Now, depending on which firmware version you have, that maximum number can either be 512 or 1024. So to compile, we select compile. It will come through and display the information that it found during the compilation. So in this case, we have references to using default names for the contact inputs, default names for the virtual outputs. So you can see they're all listed here. Some function is not enabled. So it displays it to you in this format. It's showing me how many lines I've used out of the possible 1024, so 35 are used. How many virtual output equations I'm using, there's 9. How many timers, and the date and time when this was compiled. We can also go ahead and clear the message screen by selecting the clear, and then this will clear the screen out completely. One of the other things that we can also look at is the I/O order tab, which will allow us to go ahead and change the order of how they're being displayed. The other tab here is the search. So this will allow you to click on the pull down and select a specific item, and allows you to go ahead and search for it. So here they're listed. If I select a specific item, double click on it, it'll take me directly to that item.
So if we go into another input, let's say LEDs, it'll list all the LEDs that are being used. Double click on it and it takes me to that screen that has that particular symbol. In this section we'll review the logic monitor. Now we're ready to go into the logic monitor. The first thing we need to do is we need to go ahead and clear any errors that we may have into the file. This settings file now has to be loaded into the relay. So to right click, we're going to need to update this SCL file. We get an error. It's asking us to close the designer. So let's go ahead and do that. And then once again, we're coming down here to right click. We're going to update the SCL file. Once this process is finished, we're going to load the settings into the relay. With the error cleared, now we can just drag and drop the settings file into our device and load the settings into the relay. Once that's complete, then we'll come back into the engineer portion and we'll come back into the monitor mode. Now let's go ahead and open up the logic monitor. You'll get this error the first time you use it. It says this offline device is not associated to an online device. Would you like to do this now? Answer yes. And down here where it says associate device with relay, select on the pull down and select the relay of choice. Once this clears, then the screen will now become active. So in this circuit, I'm going to be closing switch A. And when the switch closes, we'll see the activity down here in the compile editor. We'll see the light turn green. If I close the second switch, then you can see that the circuit is complete. Once the timer is completed, then you see the entire circuit going green. If I close switch number 2, then the circuit becomes incomplete and everything should extinguish. My control push button, if I switch that on, to press and hold it, then that too should enable the circuit. So during the entire process, you can see everything that is occurring, which outputs and inputs are being altered. It's creating a record of it. So in using the flex elements and the flex analog in the monitor mode, you'll see the signal and the magnitude, and you'll see a percentage of per unit on the flex element. What I've done here is this flex element operate signal has been put in as an input signal and to control a virtual output. And the same thing here, this virtual output, this flex element number 2 is also monitoring the operate signal here as an input into another virtual output. As I increase my voltage, the pickup is 1 per unit. Once I hit the 1 per unit, then everything will turn green. If I've forgotten what these elements are, what these different levels are, I can come back into the E mode here. So this is editor mode and monitor mode. If I hit editor mode, it allows me to come back in here, I can view my changes, see what they are. So this one was absolute, level, over. The second one, same thing, absolute value, level, over, 1 per unit, and they both react the same way. If I want to go back into live mode, select the M. This brings it back into monitor mode. If I reduce the voltage, then they both reduce. So now what we're going to do is we're going to make some changes in the flex element configuration. We have one input that's going to the plus N. In this one, on the second flex element, we have the signal coming into the minus N, the inverted input signal. So what we're going to do is we're going to go back into editor mode, and we're going to make the change here to make this as assigned. The first one will make it level, over, 1.0 per unit. And the second flex element will make it signed as well, but what we'll do is we'll make a small change, make this under, and this will be minus 1.00. Now for the setting to take place, once again we're going to need to compile to save it to the settings. Once the compiling is finished, we're going to write the settings to the relay. So right click, select write settings to device. We'll select our device, our connection point, select send, and we'll upload the setting into the relay. With the setting installed, we'll come back into monitor mode by selecting the M. And what I'll do is I'll slowly increase the voltage input. And now you can see that on the upper flex element, we have a positive magnitude being displayed per unit, and on the lower one we have a negative per unit being displayed. If we exceed the 1 per unit level, then they'll both operate. Here's our example of the synchro, where we have two voltages being compared, one going into the positive input, the other one going into the inverted input. This element is, if we go into editor mode, we can see that it's set up as absolute values, level. If we go over the 0.1 per unit, then this element is going to operate. So let's go back into monitor mode. So here we can see the reading is 0.08 per unit. As we make the difference between the two voltages greater, then the element will operate. If we increase it, we get closer, regardless which direction we go in. It will clear. In our volatile latch, we'll turn on contact input number 3. This is our set. You can see it's active. If I turn on switch number 4, which is connected to the reset, you can see that the output has been turned off, it's reset. If I turn off input number 3, it's still reset. If I turn off input number 4, it is still reset. Our non-volatile latch has been configured for reset dominant. Let's go back to monitor mode. So if they're both off, then the output off signal is active. If I turn on switch 3, then we can see that the on is active. If we switch on number 4, everything is turned off again, so everything is reset. If I turn off input number 3, it remains reset, and turning off input number 4, again everything remains reset. The set dominant latch, let's go to editor mode. Here we can see that it's been set to set dominant. With both switches off, then the off is active. If we switch on the set, then of course the on is active. If we close switch number 4, then it remains on. If we turn off switch 3, then of course it resets, and if they're both off, it remains reset. Now here we have the example with the different protection elements inputting into an OR gate to trigger the oscillography, one with OneShots at the bottom here and one without. So what I'm going to do is I'm going to increase the current so you can see the operation. Now let's go into the event recorder to view the information based on this. Now in the event recorder, we can see that the instantaneous overcurrent picked up and then operated. Our VO8 is their oscillography. Then there's their oscillography with the one shot. It came on, it went off. Then the TOC picked up and operated. And with the one shot, it went on and went off. You don't see another signal for the VO8. So another good reason to use the one shot as part of the oscillography triggering. In this section, I will look at the Preferences menu and the effect it has on the FlexLogic editor and compiler. The Preferences screen is located under Files, Preferences, and we'll go through not all the menus, but the ones that are of importance to us. The message colors, these colors are in reference to the compiler. This color is the background, the regular messages, and different types of warnings and errors. You can pick and choose whatever color you want to use. So by clicking on the pull down, you can go in and change the color to any choice that you wish. The next thing we'll look at, the Logic Designer Workbook. To expand on here, this is determined the size of the canvas. The units of measurements are in inches, feet, yards, miles, so forth, so on. And we can also adjust the canvas size. The default is 17 by 11. The workbook, this is for printing. You can adjust the size of your print. You can indicate which items you would like to add and different notes. In the file information, this is where you have your settings for your file. You can place your company name in here, who the owner is, version, and it'll also record the date that was modified, created, and then you can also add in a logo with this acceptable size, 36 wide by 30 pixels high. Under Logic Design or Display, we have the ability to change the appearance of these symbols from the IEC standard, ISO standard, or the UR setup. So let me just show you what the differences are. This is the UR setup. If I bring in any gate, let's say an OR gate, so this is the appearance for the UR setup. If I change this now to the ISO, it has this appearance. And if I go back and change it to the IEC, it has this type of appearance. The other things that are on that screen, also the symbol colors can either be in color or just plain black and white, or we can change the operation from just the workbook or sheet only. In the editor screen, we have the ability to select the repeat symbol. So that means that when we select an item in the toolbox, we don't have to keep coming back into the toolbox to reselect it. If once we bring it onto the canvas, we can click on it again, and it'll do an automatic repeat. The first available IO timer setting here, what it does, if you have this selected, what it'll do is it'll assign the next available value to the virtual output or the timer. If you have it unselected, then it maintains the number that's been assigned to it, the one that you selected. Once again, you cannot repeat the virtual outputs or the timers. Can't be duplicated for different circuits. So this is why it's kind of important to keep this checked off. The last item here is the auto save. So if you're creating your logic and you would like to have the auto save occur after a certain amount of times, you can adjust this. In the auto populate screen, we have a choice here to set up how many virtual outputs we'll allow per worksheet. This is to basically evenly distribute the number of virtual outputs that are available, so we can limit the number that are going out per worksheet. In the lower portion here, we have how the information is going to be displayed. With the show unchecked on these 4 columns, in this column, it will set up our sheets with the 4 defaults, and then I was adding them as I needed, and it would display the number of LEDs and contacts and communications that are unused. If we go ahead and check these off, what this will do is it'll relabel the tabs and categorize the individual components. So there will be the first tab will be LEDs, the second will be identified as contacts, the third one will be grouped into communications, the fourth one will be grouped into elements, and then the fifth one will be a sheet. So if we select OK, and now we close this down and reopen it, we'll see that the workbook has been recategorized. We've got LEDs, we have our contacts, we have our communication devices, we have our elements, and we have our sheet with our different circuits on it. In the compiler screen, here we have this acts as a filter where we can determine what we want displayed in the compiler errors. We have choices for the minor, major, and settings type errors. The automatic sort virtual outputs. This is used to give the best results and the quickest performance. The algorithm that's designed around this will rearrange the circuitry to get the best performance out of the FlexLogic circuitry. Now this setting also takes precedence over the manual configuration that we have here in the I/O order. The last item we have here is the optimized compiled output, and what this does is it optimizes the logic diagrams to reduce the space and to free up some of the FlexLogic entries. So next, the logic monitor under display displays the colors when the element is on, so the state on. There's no color for the state off. However, for the state unknown, you can also adjust the color. Under timing, we have a bunch of different things here. The first one here is show timing in an output window. So this enables to display times in a monitoring window. So because of the update rate of the logic monitoring, the timing information cannot be used as an accurate representation of the events that occur within a relay. So instead, use the device's event recorder. The timing information can be delayed by as much as 30 seconds. To save timing information to CSV, so this enables you to write the timing information into a spreadsheet. So the timing information is recorded in a text file that uses commas to separate each of the fields, and this file uses the extension CSV that is supported by any spreadsheet application. Down here you can select and filter which types of IOs and items that you would like to record the timing for. In this section, we'll take a look at the FlexLogic equation editor. The FlexLogic equation editor is located under the FlexLogic section. It's available both in the offline menu and the online menu. Both the logic designer and the equation editor cannot be opened at the same time. If we try and open up this menu, we can see the data, but everything is grayed out. We can't make any changes to it. So the first thing to do is close this down. We have to close down our logic designer, and then we can reopen up our logic equation editor. All the information that was created in the logic designer also appears here as well. So you can see all the circuits that were created. To view the information, you select View, either from the type or from the syntax, and it will show you the view portion of it, where you can see the inputs, the gates, timers, and the virtual outputs that they've been assigned to. To create a circuit using the FlexLogic equation editor, double click on it, and we're going to generate two inputs. We're going to AND them together to generate a virtual output. Now this is using the reverse Polish notation. We have to put our inputs in first, then our operands, first our operands, then our operator, and then finally the output, the virtual output. So the first one is our contact input. The second one, I'll use another contact input. I'll use a different one. And now the operator. This will be our AND function. And to finally close it off, last line to close off the subroutine is the assign virtual output. We'll create another circuit for protection. So what we'll do is we'll take the an IOC and a TOC function. So we'll press the letter P until we get down to the protection element of choice. Pressing the letter P again. And we're going to OR these together. And then we'll assign this to a virtual output. You can see this virtual output has become red because the guidelines are in FlexLogic that we cannot duplicate. We can assign the same virtual output to two different equations. So we'll assign this to the second one, and this one clears. To view it, select View. And there we can see our inputs, so our operands, our operator, and then our virtual output. And then we can select save, and this will save it into the file. After loading this setting into the relay, we can look at it from the online window. And the appearance is similar. The only thing that it has done is it's added the date to when the change occurred. Selecting view still provides the same view, where you can see the inputs, the operator, and the virtual outputs. This does not give a live representation of the status of the inputs or the virtual outputs. If you make any changes here, so when you right click, you can copy a circuit, you can paste, you can insert, you can also delete. So if I wanted to duplicate this circuit, I can. So I hit Control C, or I can do a copy and come down here and do paste. The only thing I have to do is make sure there's no duplication on the virtual output. I'll make the necessary change. And then when I save it, this will be saved directly into the relay. The information is now updated, indicating the date and time when the changes were last saved and completed. In this section, we'll discuss resources where you can find more information about FlexLogic. Information about FlexLogic can be found in any of the UR family of manuals. In section 5.6 of the manual, there's a section dedicated to FlexLogic. It describes the operand and operator types that are available in the UR. FlexLogic rules are outlined in detail, as well as how the FlexLogic equations are evaluated. There are detailed FlexLogic examples that provide explanation on the configuration of FlexLogic circuits. In this section, I want to show you how easy it is to create circuits using different symbols. In this exercise, we're going to generate a trip close circuit. We're going to start off with the trip circuit, which consists of a phase IOC protection element and a remote trip with a virtual input. So we'll start off with the protection element. Make sure that it's turned on. The second input will be a virtual input. I'll give it a name, make sure it's enabled. I'll give it a name. We'll introduce an OR gate. And a virtual output. And and a contact output. We'll connect to the operate. We'll introduce some LEDs. So this is the idea here. And we'll call this, double click on it, and give it a name. We'll rename the virtual output as well. So we can go ahead and do some alignment here. All right, we'll do some alignment here at the top as well. Alignment this way as well, horizontally. And now let's go ahead and duplicate the circuit. So I'm just doing a copy, and I'm just going to move everything down here. This will be my closed circuit. So this will now, I'll change this. This will be another virtual input. This one will be my close breaker. Number 2. This one I'll delete. This is going to be a manual close. So I'll use a contact input. I'll go with a different LED completely. Go to the second column. I'll rename this. This is my closed circuit. And my contact output will be my breaker close. And there's our entire circuit. So let's go ahead and compile. Let's confirm our contact inputs. Just going to adjust the threshold, make sure it's correct for what I need. And then now we can save the settings to the relay. And let's go into monitor mode. Let's verify that the overcurrent condition is working. We can test the virtual input circuit as well. We can also verify the closed circuit's working, close switch 3. Go ahead and close switch 1. Turn off switch 1, and then I'll close virtual input number 2. And then that shows us that that circuit is complete as well. The output contactor has also closed, so we see which LEDs are switched on as well. In this exercise, we're going to create a sync circuit using flex analogs on flex elements, and we're going to AND 3 sets of circuits together to create a sync signal. So first we'll start off with 2 flex analog signals. And we'll introduce a flex element. Now let's go ahead and duplicate these by highlighting everything, holding down the control key. Just going to create another circuit. And we'll do it again. So now we've got 3 identical circuits. The only thing we need to do is just to align them. And then we can also align these as well. And we'll introduce an AND gate. And a virtual output. So the first one's going to be a voltage. Source 1, we'll do VAG. The second one will be source 2. The next one will be frequency. And
This is located under miscellaneous. And the last one will be the phase angle for the voltage. Just verifying my information. Great. The flex analog, so the first one will be, it's already been named voltage. I'm going to set up as an absolute value, a level under, and I'll set it up as 0.2 per unit. So for less than that, then this circuit will be complete. The second one is frequency. Done the same thing, set it up with the name frequency, absolute level under. If it's less than 0.1, the operate signal will energize, will become active. And the last one is the phase angle. I've made it a little bit larger. Absolute, level, and under. Same concept. So we'll tie all these together. First thing I need to do is get rid of this. Change this from a 2 input to a 3 input. Double click on it. Change it from 2 to 3. And let's tie in the signals. Last but not least, the virtual output. Giving it a name of sync OK. And we'll just do that. Then we can align these as well. There, let's go ahead and compile. And we'll write the settings to the relay. Let's go into monitor mode. And so what I've done here is I've got two sources. You can see the magnitudes on source 1 and source 2, the frequency and the phase angle. So as long as they're not less than the comparator, the signal will not become active. Now as I slowly increase the voltage and I slowly start getting close to our configuration, then all three are now synced and the sync OK signal is now active. If the signal goes higher, then we'll lose our sync signal again. In this exercise, we're going to create an oscillator circuit to be an input to a breaker counter, and we're going to use a control push button to reset it, and then we're going to monitor the outputs when it's below the threshold for the count, when it's equal to the count, and when it's above for the count, they'll be assigned to an LED, a different LED. So let's begin with creating the oscillator circuit first. The oscillator circuit is generated in this format, where we take our input, and this becomes our virtual output. Let's go ahead and give it a name. So this will be, we'll just call it oscillator. Then we'll introduce an inverter, or NOT gate. We're going to need a timer. And also a virtual output. This virtual output and the input to the circuit has to be the same one. So let's connect everything. Once again, I'm double clicking on the timer. We can adjust the timer for milliseconds, seconds, or minutes. Let's make sure that this is seconds. And what we're going to do is we're going to duplicate this input, and this will be the input to our timer, or sorry, to our counter. We'll use a push button to be the reset mechanism. Let's go push button number 2. Let's make sure it's turned on. The function is disabled. We'll need to enable it. So let's introduce this into the reset circuit. We're going to assign LEDs to the outputs of the counter. So I'll make number 4 the high, 5 will be the equal, and the 6 will be below that threshold. In the counter, we can give it a name. And the compare, the number is going to be the threshold. Let's make it something simple as 5. And this is our circuit. So as the oscillator starts free running, every 5 seconds we're going to get an update here, and we're going to see the count here as well. And depending on the status compared to the compare signal, which is in our case is 5, will depend on which LED is eliminated. So let's go ahead and compile. And now we'll rate the settings to the device.
let's go ahead into monitor mode. So you can see the counter incrementing. Right now it's still below the 5 threshold. So now the counter is at 5. We've gone to the equal output, and on the count of 6 we should be going to the high. We're above. If I press the control push button, number 2, it resets it and the count begins again. This recap will be covered in this e-learning module. FlexLogic uses reverse Polish notation. That means we have inputs first, and then we have the operator, and then the resultant from the operator goes into an output. Logic gates require a digital input operand. Flex elements require an analog input operand. LEDs cannot be assigned to the logic gates. LEDs can only be physically connected to a virtual output or any of the inputs, never to a gate. Each timer can only be used once. So if you have different circuits, you need to assign a different timer. There are 32 timers to choose from. Each virtual output can only be used once to terminate an equation. Virtual outputs can also be used as an input to another equation. So as you saw in the oscillator circuit, we were able to take the same virtual output, use it as an input into the circuit, and have it feed on itself. Compiling saves the FlexLogic equations into the settings file. If you create your logic and you do not compile it, it will not be saved into the settings file. Each change in the FlexLogic equation must be compiled prior to loading to the relay. So you make a change in your FlexLogic, you have to compile it, and you're in the offline window, you need to upload it to the relay. You must draw a line between the various components to complete the equation. They're not there just for aesthetics. They physically connect the different components together. If you're drawing your lines between the components and you miss the connection point, sometimes it gets into a loop where as you're clicking the mouse, you'll draw a bunch of triangles and it just won't end. Pressing escape won't stop it. Don't panic. What you need to do is just press the right mouse button and that'll delete the line. Volatile latches, SR outputs will reset when the control power is lost or when it's removed. It's reset dominant. Non-volatile latches will maintain their last state when the control power is removed. Now, once again, non-volatile latches can be configured for both set dominant and reset dominant. Positive one-shot triggers are recommended when creating logic to trigger the oscillography. If you have multiple protection elements that are going off back to back, you want to make sure that the oscillography captures the waveform for each condition. The operator must be connected to a virtual output. Remember, the virtual output terminates the equation. It has to be connected to a virtual output. Logic circuits can be copied and pasted into the logic designer of a different application. So if you have some logic and say a feeder circuit, you can copy and paste it into a different logic designer and just paste it into your other circuit. The FlexLogic equation editor is disabled if the logic designer or logic monitor is active. So the logic equation editor is the older way of doing things that was prior to the logic designer and logic monitor feature. The two of them can't be active at the same time. The logic designer has the higher priority. The logic equation editor will only allow you to view the logic. It won't let you, well, it'll allow you to view the logic, but it won't allow you to do any editing. This concludes this module. Thank you so much for watching.